So, good morning, everyone. Welcome back to the second day of the 10th Amazonia Workshop on Gravity and Analog Models. We will start this morning session with the short course given by Héctor Olivares, titled Synthetic Images of Black Holes and Exotic Compact Objects.
Great. Thank you very much. Is this working? It's better. Okay. Well, thank you very much for the introduction, and also thanks to the organizer for inviting me to give this course. So, so I should start by saying that the idea of this course is to combine theory and practice. So there are 5 hours total in of the duration of the course. And for the first 2 sessions, that last 2 hours, I would like to have more or less 1 hour of theory. And then for the second part, I would like to have more or less 1 hour of practice. So in that section, we will download a code and try to run some things related to the topic of the course. So also I will try to do a small space between the first half and the second half, so that maybe we can refresh us a bit before continuing. But let's get into the topic. So, well, this is we are living really in a very nice time for the exploration of strong gravity environments. So from one side, we have the detection of gravitational waves that happened during the last decade. But also during the last decade, we had the first images of supermassive black holes at event horizon scales. So these images, we have been able to image 2 of the nearest supermassive black holes, namely Sagittarius A star and M87. And we have been able to image them at the radio frequencies of 230 gigahertz. And the information that we know about them is in total intensity of radiation and also in polarization. Now, these are the images that have been published and that are most widely known within the general public. But it is important to mention that the actual observations that we have are in a bit less intuitive way, in a little less intuitive presentation, which is as amplitude and phases in the Fourier plane. So this is just due to the nature of how observations are done, which is something that I will explain more in the sessions of tomorrow. But the important thing to keep in mind is that these images are reconstructions from observations in a different space that are obtained using interferometry. So, well, however, the present is already very interesting, and the future also points to be extremely interesting as well. So, in addition to the existing network of the Event Horizon Telescope that has produced the images that I showed you, there are a set of ongoing or proposed projects that aim to extend this array in order to observe the same systems with more capabilities, or even be able to observe other new systems. So one of these extensions is the so-called next generation EHT or NGHT, that contains shorter baselengths that will allow to sample a bit more extended structures around M87. For example, we may be able to see the jet eventually. Also, they will enhance the coverage in time so that we will be able to still have images of these sources when the Earth is in positions that are currently unpopulated, and this will allow better images of, for example, Sagittarius A star that can lead to the production of more high-quality movies. And there are also projects that combine space located antennas with Earth-located antennas, or that combine purely Earth-located antennas. Sorry, purely space-based antennas.
Can I ask a question? So,
Sure.
These projects
Currently, none of the projects that are that involve stations in space have obtained funding. So some of them are quite promising, but the expectation is that we should see this in more or less in the next decade, in the decade of the 2030s to 2040s. On the other hand, for the NGHT, some of the additional stations have already granted funding, and some of them are already in construction. Yes. And well, this will bring very nice changes, especially the use of space-based stations will hopefully increase the number of sources that we are currently able to observe. So currently we have only Sagittarius XR and MET7, but we expect 3 times increase in resolution, and this may allow to see other supermassive black hole candidates, provided that the environment that surrounds them is optically seen. So, but well, I just started talking about the environment, and this actually brings me to the main topic of these lectures. So the images that I have shown before can help us to constrain gravity, but they can also help us to constrain the properties of the environment that surrounds black holes. And the two so the two aspects of the problem are not completely separate from each other. We need to understand a bit about the environment in order to use these observations to constrain gravitation, and we also need some assumptions from gravitation in order to constrain what is the environment. So as it happens with many experimental and observational matters, the two things are not completely independent from each other. But as we will see later during these sessions, this is something that actually we can disentangle to some extent. So, however, one of the most useful tools in order to interpret the observations that the EHT produces are simulations. Actually, the way we constrain, for example, the size of the shadow that was observed was by comparing the observations with a library of simulated models. So we can produce images out of general relativistic magnetohydrodynamic simulations, or GRMHD simulations that simulate the flow of the plasma around black holes, and we can vary the parameters of these simulations in order to compare them with the actual observations. By doing this, yes.
The 60,000 images that you mentioned, are they all produced with back or a variety of codes?
So this 60,000. This library of 60,000 images was produced with 2 codes. One of them was BAC, and the other one was HARM, that now more recently has a different name. Well, it has evolved into another code that is called Karma. But actually, this number is a bit outdated. So now we have something like, I would say, of the order of million of images. And there are other codes that have started to be used to produce images for the HT library. So there is, for example, Athena, and right now I cannot I cannot remember the name of other code. So it is Hammer. So Athena and Hammer are also participating in this. There is another code that is called Coral that is also contributing to the library. So right now there are several codes that are available and that are more or less independent with slightly different formulations of the equations. So the idea of this is that the interpretation is not biased by the use of some particular code. However, on the other side, these codes have also been tested among each other in order to ensure that they produce the same solution when simulating the same physical problem.
And there is no tension between the codes?
I don't think so. No. So there is no. So there are some differences, but there is no important tensions between the codes. Although there is some tensions between the different libraries produced with different codes, But I think this is mainly due to the use of different parameters. So for example, different adiabatic indices of the plasma and so on. But maybe we can talk about this more in the later in these sessions. So, well, as I was mentioning, these comparisons with the library of simulated observations have already provided very constraining, this is to say this library of simulations already possess a large constraining power by combining the EHT observations with multi-wavelength data. So this is already not so recent, because now there are also constraints based on polarization, but this is from the theory paper from 2022 about the simulations of the observations for Sagittarius A star performed in the year of 2017. And here there are models, different sets of models that are colored according to how well they perform against the constraints given by observations. So we will speak about this in more detail in the next slides. But here on the top row, there are the models that belong to the category that are called sane. And in the bottom row, there are the models that belong to the category that is known as MAT. We also have different spins in each pizza plot. There are different inclination angles. And there are different ratios between the proton or ion and electron temperature that is represented by the radius of these pizza plots. So, well, already with these still limited observations that we currently have, these constraints show that there is only a very limited set of models that pass the constraints. This is for relatively high inclination, and all of them are in the MAT regime, and all of them have only a single temperature ratio between ions and electrons. So well, the constraining power of these models is already very impressive. On the other hand, another thing to take into account is the fact that so far all of these models belong to a single category, or well, not precisely to a single category. You know, so there are two categories, but they start from simulation setups that are very similar. So in all of them, we initialize a torus of matters, of plasma surrounding the black hole. We perturb it, and it reaches a turbulent state. But still, well, the final state preserves a lot of the symmetries of the initial torus. So one ongoing effort is to go away from these models. Also, another limitation could be that presently a very vast majority of the models that exist in the HT library consist of accretion onto Kerr black holes. So considering different types of black holes, or considering objects different from black holes, is another direction onto which this could be extended. But this is something that I will also talk about, especially in the third session of the lectures.
Can I ask a question?
Sure.
Maybe you will expand on this, but since you mentioned it, when these models fail to meet the constraints, what are the constraints we are talking about from the images that they fail to meet? Is it the shadow size, the kind of, so what is it?
It can be different constraints from different models. So, well, one of the main constraints is the size of the shadow. So this is one of the HT constraints. Or actually, what is measured is not the size of the shadow, because that is hard to measure. But what is measured is the size of the ring, of the bright ring. So this is one constraint. But there are also multi-wavelength constraints. For example, for the case of M87, we require that simulations are able to produce a luminous enough jet. For Sagittarius A star, we don't have that constraint, but that is there for M87. Or there are also constraints on the total flux of radiation at different wavelengths. So, for example, at other radio wavelengths, but also at infrared, and also in X-rays and gamma rays. So there are constraints based on the spectrum, on the morphology, and there are also constraints based on the variability. So, and for example, one of the difference between SAINS and MATS resides precisely on the variability. But so we will talk a bit. Yes. Right. So well, despite these limitations of the libraries that I mentioned, there is a set of assumptions, or actually, well, a set of conditions on which we are more or less sure about the environment of black holes, and we are sure before making the observations of the HT. So this is information that one can obtain, for example, from the spectrum or from other observations that constrain the mass accretion rate at larger wavelengths. So this information allows us to perform some simplifying assumptions on how the plasma around the black hole should behave. For example, something that we know is that the black hole mass is much bigger compared to the mass of the accretion disk. We know this because well, Sagittarius star and M87 weigh millions of solar masses, or in the case of M87, even thousands of millions of solar masses. And the plasma that surrounds them is very tenuous. So here I wrote 100 particles per cubic centimeter. It can go perhaps to even 1 million particles per cubic centimeter, but this is also something that is extremely tenuous. So from this we know that plasmas most likely or very hardly affect the background metric. So this allows us to consider that for simulations we will always use stationary spacetimes. Also, the fact that the plasmas are so tenuous allows us to use ideal gas thermodynamics. We also believe that well, because of these conditions, that the plasmas are very tenuous, but also combined with the fact that we expect a lot of ionizing radiation along, around these supermassive black holes. So because of this, plasma should be very ionized. It should, and therefore also very electrical, very conducting electrically. So this allows us to use ideal magnetohydrodynamics. So, well, here I wrote resistive, but perhaps. So for the conditions that we have in Sagittarius star and M87, it is mostly ideal magnetohydrodynamics. So plasmas are expected to be very, very conducting. And finally, we can also make estimations on the time scale that these plasmas will take to cool down via the emission of radiation. So because these time scales are much larger compared to the time that it will take for plasma to get accreted by the black hole, we can safely consider that plasmas are radiatively inefficient. And this allows us to decouple radiation from the behavior of the plasma. So we can consider separately radiation from the MHD. So by performing this separation of time scales and length scales, one can construct a procedure to go from a space-time model into some predicted synthetic observations in which it is possible to consider every step separately. So this is how the models in the library are created. We start first from a space-time model. This can be determined by the gravity theory and the nature of the compact object. It can be, for example, if we consider a black hole or something more exotic or a different kind of black hole. Then once we select the nature of the spacetime, we can use it as a background in order to perform the simulations on the behavior of the plasma. So for this stage, we perform general relativistic magnetohydrodynamics or GRMHD simulations. Then when we have performed one of these simulations, because the radiation is decoupled from the plasma, we can perform then general relativistic radiative transfer calculations. So in this step, we simulate how the radiation that the plasma emits behaves and propagates. And finally, when we obtain an image, we incorporate the uncertainties associated to the instruments and the observing conditions in order to produce a synthetic image. And also, I should say that apart from this figure, all of the the rest of the figures that I showed in these slides corresponds to synthetic observations, or actually correspond to the simulation process. So this is a volume rendering of an actual plasma simulation performed with the code that we will learn in the second half of today. Then this is an image produced with from a GRT simulation, performed with the code that we will learn tomorrow in the second half of tomorrow's lecture. And finally, this is a synthetic image also of a simulation. So this is not the actual image that was obtained by DHC, but it's a simulated image. And so this will not learn how to do, but we will learn the basics of how this is done. So, then after this introduction, this takes us to the plan of these lectures. So in today's session, I will explain how to produce GRMHD models of hot accretion flows. So a bit about how the environment so we already saw that, but with a bit more of detail, how the environment tells us what we should simulate. And also the basics about the numerical methods that are used to do that. In tomorrow's sessions, we will talk about general relativistic radiative transfer. So same we will learn about the basic radiation processes and how that connects to the image that we will observe, and also a little about the numerical methods. For this, I know that there may be some overlap with the lectures that you already had yesterday from, I forgot his name, from Gonzalo Olmos. So perhaps we will go a bit quickly through that, we will see. And finally, session 3, that will be the day after tomorrow, will be more theoretical. So it will not be, we will not work with a code, but I will show you particular applications of the pipeline that we will learn for the case of simulating the appearance of exotic compact objects. So, then let's get into the matter of today's session. So, as mentioned briefly before, we will consider accretion on two objects similar to Sagittarius A star and M87. So the plasma that surrounds this object is expected to be in an accretion pattern that is known as hot accretion flows. These accretion flows are expected to have a relatively high angular momentum, so that matter is rotationally supported, and they are expected to be radiatively inefficient, as for the reason that we mentioned below. So the time scale that it takes for the plasma to cool is much larger compared to the time that it takes to accrete onto the black hole. So the plasma stays with its energy, and most of energy transport happens because the plasma moves. So energy moves with the plasma. That is what is called advection. So the advection of energy. And in the literature, these type of plasmas are called RIAFs. That stands precisely by radiatively inefficient accretion flow. Because plasma carries most of the energy with it, a lot of the energy is in the form of plasma internal energy. So internal energy is related to pressure, as we know from the ideal equation of state, and therefore the pressure support increases the scale height of the disk. So that is why these kind of disks are always expected to be thick disks. So geometrically thick. Also, because the plasma interacts very weakly with radiation, this means that plasmas are relatively transparent. And because they are relatively transparent, the technical term from this is to say that they are optically thin. So the plasma that surrounds Sagittarius A star and M87 are geometrically thick and optically thin. So the optical thickness in general will depend on the relation between the actual mass accretion rate and the Eddington accretion rate. The Eddington accretion rate is a critical value of the accretion rate for which the plasma starts to be stopped by radiation pressure that is produced by the same accretion flow. So it is a number that depends on the mass of the black hole and is used to parameterize how important is radiation for these accretion flows. So for M87, the actual accretion rate is believed to be more or less 2 times 10 to the minus 5, the Eddington accretion rate. And for Sagittarius A star, it is thought to be also roughly 2 times 10, but now to the minus 10 times the Eddington accretion rate. So for both Sagittarius A star and M87, the plasma is expected to be very insensitive to radiation. But for M87, it is a bit less than for Sagittarius A star. So in M87, radiation could be a bit more important if one considers longer timescales.
Can I ask you how these numbers are estimated and if there are big error bars in them, these accretion rates?
Mm-hmm. Well, the mass accretion, the Eddington accretion rate comes from a first principle calculations. So it's well, the actual accretion rate for Sagittarius A star and M87 comes, so it comes from different observations, but it comes mainly from the observations of Chandra. So Chandra observes the X-rays of the plasma of the plasma medium where Sagittarius A star and M87 is. And from that, it is possible to calculate the temperature of the plasma, or something like a medium temperature of the plasma that surrounds them, because 1 pixel of Chandra is something like 10 to the 5 gravitational radii for both of them. So from there, one can get the temperature, and combining information, one can also get the plasma density, or at least the column density. So, well, from there, one can fit a model that is called the Bondi model, that is for spherical accretion, and from there, one can calculate one can calculate several parameters, among which one can estimate the mass accretion rate. And about the error bars, I think so this naturally needs to have an associated error, but I don't know. I don't think, for example, that that is an error in the order of magnitude. Mm-hmm.
And if I may ask another question, so then if you are close to the Eddington accretion rate, that means that the radiatively inefficient hypothesis falls.
That's correct. Mm-hmm. The particles that compose the plasma. So they come. So this depends. For M87, it is not very well understood, because, well, M87 is farther away and it is harder to observe. But for Sagittarius A star, this is expected to come mainly from stellar winds. So there is a group of Wolf-Rayet stars that orbits Sagittarius A star. So Wolf-Rayet stars are very windy, and most of the plasma. Sorry, the Wolf-Rayet stars. Wolf-Rayet. So these stars are very windy, and most of the accretion flow that gets into Sagittarius A star is supposed to come from these stars. Yes, they are emitting winds. So in the same way as the sun is emitting winds, these stars are emitting winds, except that Wolf-Rayet stars emit a lot more winds than the sun. Exactly, right. So the plasma then that reaches Sagittarius A star is thought to come mostly from these stars. So for M87, it is less constrained, but so people have also constructed models of how plasma gets into the black hole in elliptical galaxies, and this is, but there are, so it is less, it is more difficult to determine it accurately because, for example, for M87, it is hard to observe individual stars, no? In contrast to Sagittarius A star, where we can observe that there is this cluster of Wolf-Rayet stars. No? Yes. Sure. Well, it is hard to estimate the mass of the accretion disk because also we don't know when, for example, when the accretion disk stops. No, but what is possible to estimate is the column density of the so of the accretion flow. No? So the integrated column density. And so this is estimated in two ways. So one is via the X-ray emissivity or the X-ray luminosity, as I mentioned before. But there is another way that is very interesting. That is through the Faraday rotation. So the magnetized plasma is expected to change the polarization of light, and then by how much it changes. One can estimate what is the column density of the plasma, and this is what allows us, for example, to estimate that this plasma should be very tenuous. So, so then we have said that these plasmas are in the radiatively inefficient accretion flow regime. That they are advection-dominated accretion flows, and that they are optically thin and geometrically thick. But now, well, this is not the whole story. No, there is some additional freedom of different types of radiatively inefficient accretion flows that one can have. And one important distinction that is made a lot in the literature and in the papers of the EHT is the distinction between matte and sane accretion flows. So, and well, as I mentioned before, these behave very differently with the observational constraints. So, sane stands for standard and normal evolution, and matte stands for magnetically arrested disk. So the standard and normal evolution means that plasmas are relatively quiet, relatively calm, and the accretion of plasma happens in a turbulent way, but more as a slow process. That is driven mainly by the magnetorotational instability. We will talk in the next slide about what is the magnetorotational instability. But so one can imagine the same disks, more or less like a quiet stream of water. No? So there is turbulence in it, but it is in general quiet. On the other hand, the magnetically arrested disk regime has a very opposite behavior. So in the magnetically arrested disk regime, there is a lot of magnetic field eruptions, and this happens because mattes are a lot more magnetized. Magnetic field accumulates near to the black hole until it reaches a critical value. When it reaches this critical value, it stops matter from coming, and one has a very different type of instability than the one that drives accretion in the same regime. So this other type of instability is similar to the Rayleigh-Taylor instability that one has between water and oil. So in this example, oil would be like the magnetic field or very magnetized material, and what that is dense, less dense. And water would be as the rest of the material, so that if you let water fall onto the oil will try to go up by buoyancy. So one will form a lot of eruptions or bubbles. in this case of magnetic magnetic flux. So saturation happens at a critical value that depends on the mass accretion rate. So this is magnetic flux, and in Lorentz Heaviside units, this happens when the ratio between the magnetic flux and the square root of the mass accretion rate is around 15. And so this is what I just said, that this is a bit similar to the Rayleigh-Taylor instability, but I will show you this in the next slide. And something interesting is that MAT seems to be in general favored by the ESG observations. So if you remember the pizza plots that I showed you before, there were only 2 spots that were green, and both of these 2 spots that are green because they pass all of the constraints are in the MAT regime. So this is an example of the 2 different types of regimes. So here in both of the images, it is not set in the scale, but it is density, what we are looking at. So the same regime is turbulent, but in general very, very calm, while the MAT regime is also is turbulent, but it has a different kind of turbulence. So there are these regions that show less density and a lot of more magnetization that precisely form these kind of bubbles that go against gravity because they want to move away by buoyancy. If one looks at the structure of the magnetic field in the meridional plane, so here meridional plane, equatorial plane, one can see that the magnetic field lines become vertical, so they cross the disk, and for this reason these are also called magnetic field bundles or flux tubes. So well, as I promised, I would talk also a bit the magnetorotational instability that is the main mechanism for angular momentum transport. Yes.
So before the HT observations, was there any expectation if the same or the MAD model would be favored based on other observations or any theory? Was it a surprise to find that MAD seems to be favored?
So there were some expectations to favor the MAT accretion regime. So there is especially there was an argument that was given by Sasha Shekovskoy. I have not seen that argument written as far as I can remember, but I remember hearing it in talks that MAT accretion should be favored because all black holes will eventually accumulate magnetic flux. No? So they will. It doesn't matter on which time scale, but at some point all of them would accumulate enough flux to be in the MAT state. So this is. So there are some criticisms to this argument. So not all people is convinced about this argument, even now that the MAT regime seems to be favored. But well, there was this pre-existent argument. Mm-hmm.
And in your analogy with water and oil, so there were these kind of patches, domains of oil going against gravity via
right.
points. So should we imagine that here in the black hole case, we have sorts of domains of plasma moving away from the black hole?
Right.
In the same way, that's what we should think of?
Right, exactly. That's the analogy. So in fact, these magnetic flux eruptions or magnetic flux tubes are one of the most how do you say? Well, they are some of the best candidates that people have for flares. So because they are also associated to when the field becomes vertical or when it moves back to normal, you have it needs to change its topology. When it changes its topology, that means that you have magnetic reconnection, and if you have magnetic reconnection, one has a lot of accelerated charged particles. This is why these are some of the best candidates for explaining flares, even if not the only ones. Also, it's also well, if we observe hotspots eventually, it is also likely that hotspots are also associated to these magnetic flux eruptions. So, okay, so then let's go back to the main mechanism that is expected to drive accretion in same disks, but also for mass or other type of disk in the farther away from the region where the magnetic flux eruptions. So we need a mechanism that gets rid of angular momentum. This is because if one just have matter orbiting around an object, just because of conservation of angular momentum, it cannot get too close. No? So it needs to get rid of the angular momentum in order to fall to smaller orbits, and this is why we need angular momentum transport. So let's see how this works, in particular for the magnetorotational instability. So in ideal MHD, one has a condition that is called the magnetic field frozen in condition. This means that the magnetic field lines need to be carried with the fluid elements. So magnetic field lines cannot cross fluid elements. And this results in a sort of magnetic tension that is kind of a restoration force of magnetic field lines. So if you distort a magnetic field line, it will try to get back as it was, a bit similar to an elastic rope or a spring. So, but let's see what happens if one has this condition on an accretion disk. So let's suppose that we start with a magnetic field line that is connecting two neighboring fluid elements. And also let's consider that the rotation profile is close to the Keplerian rotation profile. So in the Keplerian rotation profile, one has lower angular velocity farther away and higher angular velocity close to the central object. So this means that if we distort the field line by perturbing the fluid elements, the magnetic field line, this magnetic tension will try to bring them together. But because it tries to bring them together, it will slow down the particle that is closer, and it will speed up the particle that is in the farther away radius. So this means that if first they were orbiting near the Keplerian speed, now the particle that is here nearby will be too slow to be sustained by centrifugal force. So now it will go even slower than what it was, because it's dragged by this other particle. And in contrast, this other particle will be too fast to be in this orbit. So so this means that it will try to escape to an orbit that is even farther away. This creates a runaway process that is called that is precisely the magnetorotational instability. And this also results in the transport of angular momentum, because the particle that goes close to the black hole will have too little angular momentum, and the particle that is outside will have too much angular momentum. So the magnetic field line is in some sense transferring angular momentum from the closer particle to the farther away particle. So, well, this will result in a runaway process, and then eventually all the magnetic field lines will be tangled, and we will have a turbulent flow where angular momentum is flowing outwards. So, well, this is the standard picture, but what happens if we compare this with the simulations that we have, for instance, from accretion from larger scales? Actually, it is there are several simulations that have simulated how the plasma behaves from when accreting from large distances onto Sagittarius A star, and the results are not so conclusive on how important the magnetorotational instability actually is. In some simulations performed by Sean Ressler, for example, it seems that some of the material is never able to circularize, and some of the accretion that one has is happening just because the winds from the stars are launched almost directly towards the black hole. So in this case, you don't even need a mechanism for angular momentum transport, because the matter since the beginning didn't have enough angular momentum to stay orbiting the black hole. But on the other hand, there is a more recent set of simulations that was performed by Jorge Cuadra, and well, this is also something ongoing. No? So before the work by Ressler, there were already simulations by Cuadra. Now there are more simulations by the same group, now led by Diego Calderón, and these simulations show that whether you form or don't form a disk seem to depend on the cooling mechanism of the plasma, which is something that is not completely well understood yet. So, well, we still take the magnetorotational instability as the main mechanism for driving accretion, but there is room still for other possibilities.
So, do I understand correctly that in this magnetorotational stability, then, fluid element is going to kind of fall down, but there's another fluid element that is going to sort of escape.
Right.
And so being transferred the angular momentum via the magnetic field lines. So part of there's an accretion towards the black hole.
Right.
But simultaneously there's an accretion away from.
That is correct. Yes. Right. So indeed, some of the matter is supposed to accrete on the black hole, and another part is supposed to fly away in what is called winds. This is different from the jets. So jets are produced by something different, but there is winds. There are also winds that are flowing away from the black hole. Right. So well, just this I was thinking of spending just little time talking about this, but this is just to link it to some previous work that I published in 2023. So just to say something about this fact that the magnetorotational instability may not be the only possible way through which accretion happens. In this year, I performed some simulations where I changed the initial condition from what is typically used in simulations for the ESG library, and here instead of initializing the simulation with a torus, I injected matter from the boundary using some reasonable prescription that emulates the interstellar medium. And by changing parameters such as the angular momentum at the boundary, the strength of perturbations, and the sonic radius, one can get a more diverse set of quasi-stationary states. Some of them resemble the disks that one has in typical simulations, especially if the angular momentum is high, but one can also have completely different accretion patterns that are from quasi-spherical accretion if the angular momentum is low but perturbations are small, up to accretion patterns that are completely dominated by shocks and filaments if the angular momentum is still small, but the perturbations from the interstellar turbulence are larger. And of course, one have combinations of the two extreme scenarios. But well, this is just to mention something a bit about my own work in going beyond the typical models you see in simulations. Well, so now we have given a background on the theory of what we expect about accretion flows surrounding supermassive black holes, and especially surrounding Sagittarius A star and M87. And now, as promised, we will talk a bit about the formulation for solving this numerically. So, well, the equations that we will need to solve are those of ideal general relativistic magnetohydrodynamics, GRMHD. These are a set of differential equations that need to be supplemented by some algebraic closure relations. The differential equations are these. So they all contain 4 divergences, so they are conservation equations. And the stuff that we will be conserving will be particle number density. So this is the conservation of particles, or the conservation of mass. We will also be solving the conservation of energy and momentum. So this is the energy momentum tensor. And we will be solving the homogeneous Maxwell equations that can be also interpreted as a conservation of magnetic flux. And we will be solving the homogeneous Maxwell equations that can be also interpreted as a conservation of magnetic flux. Exactly. No, well, radiatively inefficient doesn't necessarily mean that you have particle annihilation. So also, for example, if you have a thin accretion disk where there is where matter is radiating and this makes the disk flatter, also that case is radiatively inefficient. But this not. But this doesn't mean that you are creating and annihilating particles. Also, the case is radiatively inefficient. But if you are, exactly, just for example, in simulations of collapsars or gamma ray bursts, one is expected to be forming neutrinos, no, or to have chemical reactions. In that case, one have to solve different conservation equations for the different species that have source terms that are associated to the chemical or nuclear reactions. So as I mentioned, these are supplemented by algebraic closure relations. So we know that the energy momentum is conserved, but we need to give a precise form of the energy momentum tensor. In this case, we have that of an ideal fluid. And we have to supplement this with an equation of state. And for the case of ideal MHD, for the case of ideal MHD, as you can see, we are not solving the inhomogeneous Maxwell equation. So this is because we are assuming that we already have a completely neutral plasma, and that every time that there is a slight imbalance in the charges in the plasma, this is balanced again almost instantaneously. So then this means that the electric fields in the plasma frame are 0. And by using that condition, that is called the condition for ideal MHD, one can recover what should be the electric field in the coordinate frame, and spare to solve one differential equation more that would be the inhomogeneous Maxwell equations. So we recover the electric fields through this formula. Sure. So epsilon is the internal energy of the flow. And what else did you ask? Sorry, epsilon and what? Epsilon is the gamma energy of the flow. And gamma. This gamma is the Lorentz factor. Right. So this is the Lorentz factor of the plasma. So if one imposes the condition that in the fluid frame the electric fields are 0, so the dual of the Faraday tensor is given by this expression, no? That has the 4 velocity of the plasma and the Lorentz factor. So the dual of the Faraday tensor is given by this expression, no? That has the right. So B is the magnetic field in the normal frame, right? And from this one can reconstruct the dual of the Faraday tensor. Normal frame. Right. So okay, so we mentioned that these are conservation equations, and there is already a numerical method or a numerical scheme that is designed precisely to solve conservation equations. And this is the finite volume scheme. So how does it work? We can formulate all of the equations that I showed previously as conservation equations. We can integrate over zones and transform this equation into an algebraic relation. So we still have the temporal derivative, but the spatial derivative we have transformed it into the evaluation of fluxes at the interfaces. So we have transformed it into an algebraic relation. So by doing this, when we are classifying variables into different sets, so we are evolving the set of conserved quantities, which are number density in the coordinate frame, covariant momentum. This is something that is related to the energy of the flow and the magnetic field. And we have numerical fluxes that tell us how the conserved quantities will flow from one region to another. And finally, because the numerical fluxes are not expressed in terms of the conservative of the conserved quantities, but in terms of another set of variables, we need a set of primitive variables that allow us to write the fluxes in terms of the conserved quantities. So in the primitive variables, we have quantities such as the particle number density in the fluid frame and the pressure, which are things that are not conserved but are needed to calculate the numerical fluxes. So how the scheme works, as I mentioned, is this: we discretize. Instead of discretizing, for example, as infinite differences, we discretize by integration. So we use the Stokes theorem, and the previously spatial derivatives now become evaluations of the fluxes in the boundaries of the control volume. So this is very nice because let's consider that we are evolving the content of a conserved quantity in this cell. So if we want to do that, we need to calculate the fluxes at the interface between these and other cells. So we then evaluate the fluxes at the cell interfaces. But now this flux is shared by this cell and this cell. So if we evolve this cell and also this cell using the same numerical flux and the interface, if we integrate the total of the conserved quantity in the domain in one snapshot, and we do it again in the next snapshot, this same flux will appear with opposite signs in the evolution equation for this cell and the evolution equation for this cell. So it will cancel out, and we will be conserving the quantity to machine precision, which is better than, for example, using the conservation that one could get using plainly finite differences. For the case of magnetic fields, one uses something that is very similar, but that is called constraint transport, that allows to conserve to machine precision the magnetic flux, but this is a bit different, and a bit more complicated to explain. But it's also related to the application of the Stokes theorem, and that the scheme allows to preserve to machine precision the Gauss law on the non-existence of magnetic monopoles. But now we have obtained we have obtained an evolution equation for the conserved quantity, but and so far everything is exact. But what we're still missing is how to calculate these fluxes, and precisely in the way of calculating these fluxes is where approximations come in. So in order to calculate fluxes that take conserved quantities from one cell to the other, we use what is called the solution of the Riemann problem. So the Riemann problem is a problem that consists on how interface between states that are piecewise constant will evolve with time. So there are different numerical ways of solving this problem, and there is even an exact solution to this problem. But the exact solution is too expensive, and we normally don't use it for codes. So we use approximate solutions for the Riemann problem, that we applied at each cell interface. But before solving the Riemann problem, we tried to interpolate what would be the values of conserved quantities at the two pairs of interfaces. This is where approximations come, and this is also where one can get models, schemes that have different levels of accuracy. So one can have, for example, reconstruction methods that are first order or second order. For example, whether they approximate the values at the interfaces by lines or by feeding a polynomial or different possibilities. So there is a variety of numerical techniques for reconstruction and also of numerical techniques for solving the Riemann problem. So then a finite volume scheme can be summarized by this loop. We start with the conserved variables at some time t, then we perform a conserved to primitive inversion. Now that we have the primitive variables, we reconstruct the quantities at the two different sides of the boundary between each cell. We solve the Riemann problem approximately, then we obtain numerical fluxes, and finally we perform time integration in order to obtain the conserved variables at time t plus delta t. So then, well, this is essentially all the theoretical explanation that I wanted to give today. So for the next half of the lecture, so for the next hour, we will be putting this in practice using a code that is called the black hole accretion code. So this code solves the equation of GRMHD in arbitrary fixed spacems. It is parallelized, so you can run it in machines as big as you want. And in fact, this code was one of the codes that was used to build the library of the EHT. It has some hybrid parallelization that allows it to work both with MPI and OpenMP. So this allows it to scale well up to order 80,000 CPUs, and well, it also uses these advanced techniques like adaptive mesh refinement, and it has machine precision fulfillment of the divergence-free constraints. So one of the nice things about this code is that it is publicly available, so you can download it from this website, and this is what we will do next. And also we try to keep it well documented and have manuals and tutorials. So, well, just to conclude, these are the takeaways from today's theories part. So the strong gravity systems that we hope to image at event horizon scale resolution are in the radiatively inefficient accretion flow regime. So the currently existing simulations have explored mainly the same and the math regime, but there are more scenarios to explore, and this is something on which we can well get into the field and try to do something new. So also modern numerical modeling uses finite volume methods. These have very nice properties. I didn't mention shock capture, but these methods are very good to capture shocks. They preserve conservation equations to machine precision, and they also preserve the constraint on non-existent magnetic monopoles to machine precision. But the price to pay is that variables have to be located at different places. So you don't have only cell-centered variables, but you have variables located at cell centers and fluxes located at the interfaces. And also one has to perform this conserved to primitive inversion that is one of the parts that takes most of the computational cost of codes. And okay, so having said that, let's have a 10-minute break or so, and then let's go back to the practical part of the session. So thank you very much. Practical part of the session. So thank you very much. Yes, well.
Thank you very much, Héctor. I'm very curious about the open code that you just showed before. And one doubt that I have is regarding the adaptability that you can use. I never have used this code. Of course, this is the first time I'm seeing it. And at least for the case of when you are computing shadows, there are many open codes already in the internet, but you have a hard time to implement numerical solutions to obtain shadows using those codes. And usually you have to build your own code to compute the shadows, to simulate the shadows, the images, astrophysical images of numerical solutions. Is this the case for this open code, or?
So actually, well, one of the goals of creating BAC was precisely to test space-time models beyond Kerr or even beyond black hole. So BAC is, I would say that this is especially good for using, so for having the freedom to use other space-time different from Kerr, and it already has a built-in module to simulate numerical space-times. So if you want, well, I was thinking that the tomorrow session, because we will talk about radiative transfer, and you may have also seen that in the other course by Olmos. Maybe we can make the session of tomorrow shorter, and perhaps if many people want, we can dedicate some time to learn how to use BAC on numerical spacetimes.
It would be nice.
Many people want, we can dedicate some time to
Thank you, Héctor.
just learn how to use BAC on numerical spacetimes.
Thank you for the question, the answer. Do we have more questions?
Thank you, Héctor.
Hi, it's just a curiosity. How far beyond a black hole can this code go? For instance, can you consider a wormhole in this kind of code to your simulations?
So, so we have never simulated wormholes with this code, but there is people that have simulated wormholes with other GRMHD codes. However, depending on the particular wormhole model, it may not be so difficult. So if you can cover the whole spacetime with a single chart, it should be very easy. Visualization may be complicated, and we may need to develop additional modules for proper visualization of wormhole spacetimes. But computing the simulation should be easy. Now, if instead you cannot cover the whole spacetime with a single chart, if you need to use two charts, then this is something that we cannot currently do. Now, if instead you cannot cover the whole spacetime with
Thank you very much. Any more questions?
Then this is something that we cannot currently do.
So if not, we will have a short break of 10 minutes, and we come back soon.
Thank you.
For the second part of the. So if not, we will have a short break of 10 minutes.